today with an hour-long talk on experimental and numerical modeling of internal solitary waves. So thank you so much for giving this talk, Magda. The floor is all yours.
Thank you very much, Daniel, and good afternoon, everybody. I'd like to begin by thanking Daniel and all of the organisers for the invitation to speak today. It's an absolute pleasure to be here, so thank you very much for having me. I'd also like to thank you all for tuning in. I appreciate we're fairly late on a Friday at the end of what I'm sure has been a very busy week for many, so thank you for making the time to come along and listen. As Dan's already said, I'm going to be talking to you about the modelling of internal solitary waves. So I'll start off with a bit of background and motivation. I'll then talk you through the experimental and numerical methods that I've been using to study such waves before moving on to some results. So the results I'm going to focus on will be for unstable internal solitary waves, bottom boundary layer, wave-induced flow, and shoaling internal waves. And then I'll finish off just by saying where I'd like to take this work in the future. The presentation is going to be mainly made up of pictures and movies, and it's going to be fairly light on technical details. So solitary waves were first discovered by John Scott Russell in 1834 on the Edinburgh to Glasgow Union Canal. Russell was watching a horse that was towing a barge. The barge came to an abrupt halt, and as it did, it set a surface solitary wave into motion. Russell followed this on horseback for quite a distance before he lost it in the winding of the canals. And what he observed was that this wave could travel a very large distance without any change of form. He later did some experiments and showed that the speed of the waves depended on the amplitude. The larger the amplitude, the faster the wave traveled. And he also showed that these waves do not merge. So if you collide two waves head on, or you do an overtaking experiment, they just pass through one another without any change in form, except for a small change in phase. So internal solitary waves are solitary waves that travel along density interfaces within stably stratified fluids, and they owe their existence to a balance between nonlinear wave steepening and linear wave dispersion. They occur in many geophysical settings, including coastal zones and river outflows, estuaries, lakes, reservoirs and fjords, the oceans and marginal seas, and also the atmosphere. We also get them in non-geophysical settings, and I've just listed some examples for you there. If anyone is interested in finding out more, there's some nice annual review fluid mechanics papers that have been published fairly recently. And again, I just reference them here at the bottom of the slide. So I'm going to concentrate on oceanic internal waves. So I'm just going to do a little bit of motivation in the context of the ocean. So we have the meridional overturning circulation. So what happens is we get solar radiation at the equator. This heats the near surface waters, which can then propagate poleward. As these waters propagate poleward, they lose heat to the atmosphere. Fresh water is also evaporated from the surface, and the fluid becomes more salty. So as a result of the water being cooler and saltier, it becomes more dense. It then sinks to the deeper parts of the ocean, and over time, it makes its way back to the equator and can be brought up to the surface again. Okay, so this conveyor belt of motion, this overturning, is very important for our weather and climate, and also there's implications obviously for biology and water quality within the ocean. Now, one of the big questions in oceanography is how does this deep, cold, salty water how is that brought back up towards the surface, and how do we close this conveyor belt? So Monk and Wunsch published a paper in the late 90s in deep sea research, and the image you see here has just been taken from their paper. They looked at the energy budget in the ocean, and they looked at all the different components that make up the energy budget. And you can see on this schematic internal waves feature. The kind of numbers associated with internal waves are relatively small in the grand scheme of things, but Monk and Wunsch also commented and showed that without the comparatively minute mechanical mixing sources, such as internal waves, then the meridional overturning circulation would not exist. Okay, so internal waves have an important role in that kind of from a fundamental physical oceanography perspective. So we know that they're a source of momentum and mixing. They can transport heat and nutrients vertically. They can resuspend sediment and transport mass over very large distances. And the three different figures you see here are all field observations. So these beautiful images are acoustic backscatter images. And you can see they show a very rich suite of fluid dynamics. I'll refer back to these images throughout the talk while we discuss some of the features that they're shown in more detail. Internal waves are also of interest from an offshore engineering point of view, as they can have impact loads on things like cables, rigs and risers. They can scour pipelines and tilt helipads. They also interfere with underwater communications. So again, in the offshore engineering context, they're of importance, and also obviously to the submariner community. They have very different properties to surface waves. So just to kind of give you a feel for what an internal solitary wave is like, I just want to very quickly talk you through some numbers. So typically they have wave speeds of the order 0.1 to 1 meter per second. They have wavefronts of the orders tens to hundreds of kilometers, wavelengths of the order 0.1 to 1 kilometer, and amplitudes of tens to hundreds of meters. So they're routinely observed in the South China Sea with amplitudes of 120 meters and fluid depths of just 340. And the world record, as far as I'm aware, was this observation by Huang et al., which was just published in 2016. They've observed an internal wave with an amplitude of 240 meters. So by that, I mean the distance that an undisturbed picnic line is displaced by the wave motion. So this vertical distance here, this maximum extent. Just to give you an idea of the kind of scale, what does that mean? I had a quick look on Google today for the tallest buildings in Europe, and I found that as of 2020, these were the tallest buildings in Europe. And you can see that the height of these buildings is the same or very close to the amplitude of these waves in the ocean. So that gives you an idea of the scale. They're really large amplitude waves within our seas. I also, as a nod to Cambridge and the fact that unfortunately we can't all be there today, had a look for what was the tallest building in Cambridge. And here's a nice photograph. It actually turns out quite fittingly that the tallest building in Cambridge is Cambridge University Library. So really fitting, a place of learning and books, is the tallest building in Cambridge. It stands at nearly 50 meters tall. So in terms of an internal wave in the ocean, we expect the amplitude to be 3 or even 5 times the height of that library. I also just want to quickly mention this observation that was made in just off the northwest Australian shelf edge by Van Gastel and others. They measured a wave of 83 meters and fluid depths of 124. So we often measure nonlinearity by the amplitude of the wave divided by the total fluid depth. And you can see that this wave is highly nonlinear. So as an internal solitary wave travels along the picnic line, sorry, one more thing I just want to quickly say is that these waves travel as rank ordered wave packets. So typically, or what you get, actually not typically, what you always get is that the leading wave has the highest amplitude, the next wave in the train has the second highest amplitude, and so on. And that's because the bigger the amplitude of the wave, the faster it travels. So if we were able to observe this wave over an infinite amount of time and there was no interaction with other waves or with shoaling or anything like that, then we'd see that this leading wave would just leave its tail behind. Okay, and as the interface is disturbed by an internal wave, we have a velocity induced at the surface. Okay, that gives rise to regions of convergence and divergence, and we get rough and slack water, which can be we can observe from space. Okay, so here we're looking at images taken from NASA's website. The first is the Lombok Strait off the coast of Indonesia. We've then got Hainan Island in the South China Sea and the Strait of Gibraltar. And in all of these images, we can see these light and dark patches on the surface of the ocean. These are surface signatures of the internal wave motion that's going on subsurface. So by using remote sensing and also in situ measurements, we can build up a picture of the global distribution of internal solitary waves. So here you can see this map just shows you where internal solitary waves have been observed, and you can see that they're very widely spread throughout the globe. They can be generated by various mechanisms. So they were first discovered by the Norwegian polar explorer, Fridtjof Nansen, in 1893. So Nansen was sailing into a fjord, and as he did, he felt something that he called the dead water effect. So his boat slowed down. He worked it out that the reason his boat was slowing down was because as he came into the fjord and he came into a stratified water column, his ship's hull was disturbing the picnic line. As it did so, it generated internal waves. In the process, it lost energy, and as a consequence, the boat felt a drag. In the ocean, they are typically generated if you have interaction between tidal currents and bottom topography. So if you imagine you have a sill or a seamount and you have your picnic line being washed up and down over that, then you get lee waves generated which propagate away from the seamount as internal solitary waves. They can also occur if you have a downwelling event or if you have gravity currents intruding. So for example, here we're looking at a SAR image, which is taken from a paper by Moom and Nash. Here we've got the mouth of a river. So coming out of this river is fresh water. So we have this buoyant plume of fresh water going into salty, brackish coastal sea. This plume of water extended deep enough that it could disturb the picnic line. As it did, it generated internal waves, and you can see in this image, the surface signature of those internal waves is being picked up and they're propagating offshore. Okay, so how do we generate these waves in the laboratory? Well, we have a wave flume. It is 7 meters long and it's 0.4 meters wide. And we begin by filling the tank with dense brine solution. So under the tank here, we have a reservoir of water, we salt it up and we pump it into the tank. Once we've done that, we have an array of sponges that we put on top of the water column, and we then gravity feed from these head tanks a less dense layer of fluid. Now, in this particular experiment, actually what we're doing is in these two tanks, one of these reservoirs has salty fluid, which is the same density as the fluid in the lower layer. The second reservoir is fresh water, and we have these two things set up in hydrostatic balance before we start the experiment. Then as we drain from the salty reservoir, we have a valve between these two, we open it up, and as we drain off, we constantly dilute from the fresh one, and in that way, we can get a linearly stratified top layer. And I'll just let this play again, and if you look closely, you'll be able to see the difference in the two layers. You have to look quite closely, it's about there. Okay, so once the tank is stratified, we remove the sponges and we put a gate in the upstream end of the tank and we fill behind the gate. So you can't see that at the minute that's going on. I'll show you a schematic diagram in a minute to show how that's used to generate internal waves. Once the stratification is complete, we have these conductivity probes that sit above the tank, and we use them to get a profile of the density field within the tank. Beneath the tank, we have a light box that makes a thin light sheet, and we switch off the lights and we record whatever experiment it is that we're doing. Okay, so here's the experimental arrangement. We have some stratification in the main tank. We insert a gate, and behind the gate, we fill a volume of fluid which has the same density as that in the top of the layer in the main section of the tank. So if you look closely, we end up therefore with a density gradient across this gate. So behind the gate, we predominantly have the fresher fluid, whereas in the main section of the tank, we predominantly have salty fluid. So when we remove the gate, the less dense fluid rises, the heavier dense fluid sinks, and this generates a disturbance on the picnic line, which propagates into the main section of the tank as an internal solitary wave of depression. And by carefully controlling the shape and size of what we put behind the gate, we can control what we get out in the tank. So to visualize the flow, we seed the water column with neutrally buoyant, light reflecting tracer particles, and we illuminate from below. So we have that thin light sheet, and we view from the side. So we're looking at a two-dimensional slice of the flow field. We record the image, and then we use a software package called Digiflow, which was developed in Cambridge by Stuart DL. And within that package, we use particle image velocimetry to compute the velocity field. So just very quickly, the way that works is we look at a given image, identify patterns on that, or in fact particles. We identify what a particle is. We then look at the next image in the sequence and use a pattern matching cross-correlation pattern matching technique to try and assess where the particle goes from one frame to the next, so we can get a displacement. We know the time interval between frames, and hence we're able to work out the velocity field. The conductivity sensors that you saw being put down through the tank, as the name suggests, they measure conductivity. Conductivity changes with salinity, and hence we're able to infer the density field. So let's take a look at a movie from the lab. So this region here where you see a congregation of particles is basically the picnic line. We have a homogeneous dense layer of fluid in the bottom, and we have a less dense layer of fluid on the top. These are those conductivity sensors that we just talked about. Now, you're looking at this in a false color scheme, because we sometimes see a little bit more with this scheme. If you were to look at this in the lab with the naked eye, you just see white dots on a black background. Let's play this, and you can see that we've got a large amplitude internal solitary wave of depression. It's going unstable, and we're taking a probe strike through those billows in the back to see what the density structure looks like within them. I'm just going to play that once more, and I'd like you to have a look at how the fluid moves both above and below the picnic line. So you can see above it goes in the same direction as the wave, whereas below it goes in the opposite direction. So there's a shear across the interface, and it's that shear which is responsible for the generation of these Kelvin-Helmholtz billows rolling up on the tail of the wave. So how do we model this? I have two numerical schemes that I use. So the first one I'm going to talk about is inviscid, and the second one includes viscous terms, but let's just look at the inviscid one first of all. So we're going to neglect viscosity. We are going to assume that the fluid is incompressible. We're going to impose the Boussinesq approximation, which Paul spoke about earlier, and assume that our fluid is two-dimensional. So the first equation you can see here is just Euler's equation. It represents conservation of momentum. The second equation is conservation of mass, and then I have an incompressibility condition. So we can re-express everything in terms of vorticity and buoyancy, and we just get that buoyancy is materially conserved, and the material derivative of vorticity is equal to the horizontal derivative of buoyancy. So weakly nonlinear theory is really well known. This audience, I'm sure, knows this theory better than what I do. It's Korteweg de Vries theory. So we can write our stream function as a waveform multiplied by some vertical structure function. The vertical structure function satisfies the Helmholtz equation. And if you expand the stratified Euler equation in terms of these two small parameters, so we've got small amplitude, long waves, we derive the KdV equation. So we can see here that we've got a balance between nonlinear steepening and linear wave dispersion, okay? And this is exactly the properties that a solitary wave has. We know that we can find solutions to this equation, and they take a set squared form. Obviously, this theory is weakly nonlinear, so we've assumed that the waves are small amplitude, but we've seen, or I've already shown you, that in the field, the amplitudes can be very, very large. We can have highly nonlinear waves, and we found in the lab, to get these things to break, we really had to push that amplitude. So we look for some fully nonlinear theory that we can use. And first of all, let me talk you through the steady state fully nonlinear work. So if we neglect time dependence, then we just get the stream function satisfies the Helmholtz equation, which I've just rewritten here. We can note that vorticity is Laplacian of the stream function. So we just get that vorticity is equal to minus the buoyancy frequency squared divided by the wave speed squared times the stream function. So we're going to try and solve this equation numerically. So we have a computational domain, which is 2 pi periodic in the x direction. It's rectangular. And we have rigid boundaries top and bottom. So we set up a computational grid within that domain, and we give the undisturbed n-squared profile as input. Okay, so we can get that from the lab. We then start with an initial guess for psi and c from the KDV theory, and we know that's really good at small amplitude. So we start with this guess at a very small amplitude. We then numerically increment A and use linear extrapolation on the previous psi and c values to get new estimates. And we just continue that process until the amplitude is such that the wavelength fills half the computational domain. So this iterative procedure that we've used to find the steady state solutions was published in JFM. It was done with Stuart King, who was my postdoc at the time, and David Drischel, who was a colleague. And full credit really should go to Stuart and David. They developed the numerical theory. So that's the steady state. Obviously, we want to know, though, how these things evolve with time. So to solve the evolution, we used a numerical solver known as CLAM. So this is a combined Lagrangian advection method, which solves the evolution of the vorticity using a combination of contour advection and a pseudospectral method. We give the code the fully nonlinear steady state fields for buoyancy and vorticity as initial input, and then we just let it go. So this code's been developed by David Drischel and others over the past 20 years or so. Okay, so here's the result. So this is just to give you an idea of the kind of qualitative agreement that we can get between the lab and the numerics. You can see it's really good. We also got very good quantitative measures. So we looked at something known as Thorpe scales through these billows. So we took the density profiles through these billows. We did a Thorpe scale analysis. We did that both numerically and experimentally, and we got excellent quantitative agreement as well as the kind of qualitative features you see that are picked up here. So what were our main findings? Well, first of all, for me, I was just really pleased that we were able to make one of these waves in the lab. So it took a lot of time and effort actually to get these waves to break. It was quite difficult. And when we did, it was really nice to see that we were replicating these features that Jim Moom and others had seen on the Oregon continental shelf back in 2003. We were able to compare what we did in the lab with some steady state numerical work. So I did this work with Dorian Fructus, John Gruer, and Atle Jensen, who are in Oslo, and with Peter Davies, who's in Dundee. And what we found was that for a wave to break, not only did you have to have shear, but you had to have it present over a given lateral extent. Even if the shear was high, if it didn't extend over a certain region, then the waves didn't break. I then developed the work numerically with Stuart and David. We were able to sweep parameter space, so we could go to parameter regimes that we couldn't in the lab, and we found that the critical parameters for the onset of instability were functions of the stratification. And then more recently with James Franklin, who was a PhD student of mine, we looked at these billows themselves, and we found that the characteristics of these billows were affected by the spatially varying wave-induced shear flow. So we did a combined numerical and experimental approach and found that the wave amplitude and the wave steepness had a crucial influence on the billow behavior. So sometimes we got billows that overran one another, other times we got them collapsing in a funny way, and that behavior was very dependent on the shape of the wave. So I'm just popping this slide back up. The reason being is I just want you to note that we've got a lot of observations of internal waves around our coastlines. So we know that internal waves at some point are going to shoal on the continental slope and shelves. There have also been some observations of these waves shoaling. So the first observation that you see here was made by Jim Moom again on the Oregon shelf. It's quite hard to see, but there's a black line here. This is an isopycnal. He's looking at an internal solitary wave which is shoaling up this slope, and associated with that shoaling, there's enhanced backscatter to the bed, suggesting that these internal waves resuspend sediment as they shoal. In the second observation, this was made in the St. Lawrence estuary, and there's a wave-induced nepheloid layer. So it's thought that this enhanced nepheloid layer is due to a shoaling internal solitary wave. And finally, in this last observation, Internal waves have been linked with the formation of sand waves. So here we're looking at the Tyrrhenian Sea. This SAR image shows the surface signature of an internal solitary wave packet. And if we look along this transect 8b, if we look at the topography in the ocean, here's that transect 8b, and you can see there's some sand waves on the bed of the ocean. So Droghe et al. Have linked this internal wave packet with the formation of these sand waves. Before I show you what we've done in terms of investigating shoaling internal waves and what others have done in the literature, I just want to take the slope out of the problem and show you what we know about the wave-induced bottom boundary layer flow over a flat bed. So we're back in the lab, and I just want you to concentrate on the flow right at the bed.
I'm going to go upstairs because the guy will come.
So as the wave propagates from left to right,
minutes.
you can see that the fluid is accelerated in the negative x direction. It then decelerates, and if you look closely, hopefully you can see here right at the bed, we have a reverse flow, this small jet going right along the bed of the tank in the same direction as the wave. So this observation was first made when I was a postdoc of Peter Davies. It was one of the first experiments I did in the lab, which is why this is horribly overexposed, but it was really nice to get a result so quickly. It was a feature we weren't expecting to see, but then of course, the fun was going away and trying to find out why that feature was there. And I want to explain to you why we think we see this flow reversal. So if we just think about this schematically in the wave frame of reference now, we've said that under the front part of the wave, the flow was accelerated in the negative x direction. So in this part of the flow, we have a favorable pressure gradient in the flow direction. We have a maximum velocity reached under the trough of the wave. And then as the wave goes past, the flow decelerates in the negative x direction. So in the second part, underneath the wave, we have an adverse pressure gradient in the flow direction. And if you have an adverse pressure gradient, you can get boundary layer separation. So I did a little bit of boundary layer theory, predicted where the boundary layer would separate, and found that it coincided with where this flow reversal began. So we attribute the formation of this prograde jet to boundary layer separation and the adverse pressure gradient region. And this was in good agreement with some previous work that Larry Reddycop and Hammond had done back in the late 90s. We've progressed this work to look and see if we could generate vortices at the bed. So Pete Diomessis and Larry Reddycop said, as well as getting this flow reversal, they would expect to see a vortex forming at the bed, which was shed upwards. So we went back into the lab to see if we could see that. And let me just show you what we found. So here, you're going to see a movie where we're zooming in on the bed. And in the top here, you're going to see output from the PIV. So these are velocity vectors. And this is obviously the raw lab image. So we're zoomed right in. We've pushed the Reynolds number of the flow. So the fluid is going faster. You can see as the wave goes past, there goes the jet. So we see the jet forming again along the bottom of the bed. And because we've got an inflection in the velocity profile, we get these vortices forming at the top of the jet. You can see that they get shed upwards into the water column and they resuspend particles off the bed of the tank. And this work was published in Physics of Fluids. And I must acknowledge Preeti Shivaram. She was a visiting student from the University of Western Australia. She was one of Greg Ivy's students, and she did a great job with us in the lab, helping to really push the Reynolds number of the flow. It was really nice, again, to get those lab observations because around the same time, there was this nice field paper that came out by Quaresma et al. On the Western Portuguese midshelf, where they had an internal solitary wave traveling on the thermocline and associated with it these observations of sediment resuspension. Okay, so now let's think about what happens if we put a slope into the problem. So there's been a lot of work done on this, and people have shown that you can get different kinds of braking when internal solitary waves shoal. So you can have surging, collapsing, and plunging. And the different kind of shoaling has been classified based on an internal Iribarren number, where the Iribarren number is defined to be the slope steepness divided by the square root of the wave steepness. And Leon Borgman and others have shown that you get a qualitative change from plunging to collapsing to surging as the Iribarren number increases. They've also shown that if you have very gentle slopes, you get fission followed by bolus formation. And you can improve the delineation if you consider variation in the Reynolds number. Okay, so a lot is known. However, all past work has concentrated on one kind of stratification. And they've looked at a stratification where you have a homogeneous bottom layer, a relatively thin pycnocline, and a homogeneous top layer. Okay, so we do get that a lot in the ocean. As you can see here, we've got an example from the Labrador Sea. However, we also know that if you change location, then the stratification changes. So for example, in the South Atlantic, you can see that the pycnocline is much more broad than what it is in the Labrador Sea. If we go to the Arabian Sea, it's even more diffuse. And in the East China Sea, the stratification is such that you've basically got a continuously stratified water column. The density is continually changing with depth. So we thought it would be interesting to look at stratification and see if changing the stratification has any effect on shoaling classification. So we've done this both numerically and also experimentally. The numerical solver that we've used is SPINS. That stands for a spectral parallel incompressible Navier-Stokes solver. So we now have a viscous term included. So this is Navier-Stokes equation, represents conservation of momentum. We have incompressibility again, and conservation of a tracer. So we have a tracer in the numerical code in case we want to look at specific densities, for example. We have no slip boundary conditions at the top and bottom of the domain, and free slip on the end walls to avoid doubly clustered grid points. So SPINS has been developed by Kevin Lamb and Marek Statzner over a number of years, and the reference is given here for the latest version of that code. Okay, so we've looked at three different kinds of stratifications. So the first stratification we considered was the thin tanch or thin pycnocline case. So this is the same as what other people have used in the literature. And the reason we started with that one was to see if we could validate our numerics. So would our numerical scheme reproduce what other people have done in this area? We're also going to look at what I'll refer to as a surface stratification, where we have a linearly stratified top layer and a homogeneous bottom layer. And we've done this both numerically and in the laboratory. And finally, we're going to look at a broad stratification where we have this very diffuse broad tanch profile to replicate something like the East China Sea, where the fluid is essentially continuously stratified throughout its depth. Okay, so these are a bit busy, but let me talk them through you as slowly as I can to try and explain what's going on here. So here we're plotting slope steepness against wave steepness. And the three different plots are for the three different stratifications that I just mentioned. So the first one is for the thin tanch profile. The different colors correspond to different shoaling types. So we have fission, plunging, collapsing, and surging. And I'll talk about this other surging example in a second. So if we look at the first plot, first of all, the plus signs and the crosses correspond to data points from previous studies in the literature. The circles correspond to our numerical simulations. So if we just compare the colors on our circles with past literature, you can see that we've got good agreement. These solid black lines are the delineations that have been published in past literature. Where they're dashed is where we don't agree. Okay, so if you look here, we got numerical runs which gave us collapsing waves, whereas past literature suggested that they should be plungers. But if you look, there was no observations made in past literature up here, so we still have agreement. It could just be that this black line should be going up there. Okay, but cut long story short, what this plot shows is that our numerics are in good agreement with previous literature for the thin tanch profile case. If we now move to the second plot, this is the plot where we had surface stratification, so that linearly stratified top layer and homogeneous fluid in the bottom. And if you just compare these two, the biggest change you can see is that these orangey colored data points are now blue. Okay, so in the thin tangent profile, where we had plunging dynamics, for this different stratification, we have collapsing dynamics. So actually we found when we had a surface stratification, we were unable to make a plunging wave. And if we come to this, oh, the other thing I should say about this one is, if you look closely, there's some filled squares on there. The filled squares are the laboratory observations, and you can see we've got really good agreement between the lab and also the numerics. And then if I come to this last one, this is where we had the broad tangent profile. And again, if you look at the colors, they've changed again. So where we had in the thin tangent, we had plungers. In the surface stratification, we had collapsers. And here we've got these ISs, which stand for unstable surging waves. So these were surging waves, but they were unstable, and I'll show you what they look like in a second. I should say these yellow observations are surging waves, and we have pretty good agreement, regardless of stratification. And also, if we look down here, these light blue ones are fission, and they didn't seem to be affected by stratification. But certainly in this region here, the shoaling dynamics are affected by the stratification type. So what I'm going to show you now are some simulations for this data point here, 9L, this one 8L, and this one 9R. So what I'm doing here is essentially fixing the slope steepness and the wave steepness, and we're just going to vary the stratification and see how that changes the dynamics. So the first example is where we have homogeneous fluid in the bottom and in the top. This panel corresponds to density. This one is horizontal velocity. This one's vertical velocity. And the color scheme here is vorticity with velocity vectors over the top. So you can see as this wave shoals, the leeward face goes to vertical and it becomes gravitationally unstable, and the wave plunges over on itself. Okay, so that's in agreement with past literature, and it's what we'd expect. If we keep the same wave steepness and the same slope steepness, but we now change the stratification, so we've now got a homogeneous layer of fluid in the bottom, and we have a linearly stratified top layer. And let's just see how things change. So now what you're going to see is that the leeward face becomes steep, but it doesn't quite plunge over on itself in the same way. Because if you look at the boundary layer, we get separation of the boundary layer, the generation of a large vortex, and the wave gets pulled back on itself before it can plunge, and we have what's known as a collapsing wave. Okay, so it would appear that by adding a density gradient to that upper layer has suppressed the ability of the wave to be able to plunge. Here's another example of a collapsing wave, this time from the lab. And this is just to show you that we get a nice agreement between the lab and the numerics. So you can see as this wave shoals, we see it steepening on that leeward face, but there we get that huge vortex generated at the bed, and the wave collapses back on itself. You can see this vortex propagates up the slope, and there's a lot of mixing going on. So the fluid goes blurry as it gets mixed. Let's take a look at the broad tangent profile now. So you can see now we've got a continuously stratified water column. Otherwise, everything else is the same. And you'll see in this case as it plays, is it even playing? Yeah, it is. So as this plays, you'll see that we actually get a surge of fluid that propagates up slope. So this time having a density gradient at the bed has suppressed boundary layer vortex formation. We get a surge of fluid, and also if you look at the top face of this surging bolus, you see we get these KH billows forming, and there's a lot, again, you'd expect a lot of mixing to be associated with that. And finally, for completeness, let me just show you an example of fission. So the three examples I just showed you were for a set Iribarren number. For the fission case, I'm changing that. We're looking at a very gentle slope. It doesn't look like it in the aspect ratio that's been plotted here, but this is actually a very gentle slope. And if I can just speed this up, as this wave comes into the slope, you can see we get a fission event, and we get these boluses of fluid being formed at the bed, which subsequently propagate up the slope. And if I forward this up, you'll see you get more than one. So there's a second and a third forming. And this kind of deep salty water is being pulled up the slope. In the laboratory, we are obviously limited by the length of the tank. So in the example I'm going to show you, it's the same as the numerical movie you've just seen, but the wave hits the end of the tank. So we don't get to see what happens to the waveform itself, but we can have a look at the bottom boundary layer dynamics. And if you look closely in this region, you'll see that we start to get, there's the jet, then we get these vortices forming, and it looks like we get 1, 2, 3 boluses of fluid that are being taken up the slope, similar to what we saw in the numerical example. Okay, so we can compare energetics between the different breaker types. So here I'm showing you a plot of the percentage of energy converted. The solid black line is when it's converted due to dissipation, and the dashed black line is when energy is converted due to mixing. The blue plots are for positive bed shear stress and negative bed shear stress. So if we just look at all of these plots and we compare the black lines, so the solid black and the dashed black, you can see that most energy converted goes to dissipation rather than to mixing. If we look at the surging and fission examples, you can see that there's very little change in the mixing or in the dissipation rate. So the other thing I should have said, apologies, which I haven't yet, is where you see these little blue crosses, this is where the wave begins to show. Okay, so if you were to look at the plot for dissipation, this line here, there's not a huge change in the gradient of that line in the surging and the fission cases. However, if you look at the plunging and collapsing, you can see that when the wave shoals, there is a marked kink in that plot. So the dissipation rate is increasing as the wave shoals. And also if you look at the collapsing one, as the wave shoals, we can see that the amount of mixing has increased as well. And that's due to that large vortex that we saw at the bed. What else do I want to say? If we look at the two surging examples, so these were for different stratifications, you can see that the dissipation is similar in both cases, but the mixing rate is much higher when we had the broad tangent profile, and that's because we had those KH billows forming on that surge of fluid that went up the slope. And finally, if we just look at the bed shear stress, we can see that there's a difference in the broad tangent case for the surging, as opposed to in the surface stratification one. So this suggests that stratification is important when it comes to assessing resuspension and sediment transport. Okay, so there's a lot in there, but let me just quickly try and pull out the main findings. So we've seen that stratification does affect the shoaling classification. The density gradient in the upper layer, if we add that density gradient, that then suppresses plunging dynamics. If we put a density gradient in the lower layer, that suppresses collapsing dynamics. And we saw we could generate these surging boluses of fluid that supported KH instabilities. So that's nice, really rich in terms of fluid dynamics, but actually if we just want to think about the field, on slope steepnesses that are representative of the continental slopes, in other words, these relatively shallow slopes, we actually expect to get fission in all these cases. So regardless of the stratification, we saw fission on slopes of this steepness. However, if we just look here, I'm just showing you the differences that you might get due to stratification. So this is a fission event for a thin tangent profile, and here we have one for a broad tangent profile. You can see, first of all, that the number of boluses are different, and there's more work to do in this area to see how things are really going to vary with that. So this work is currently under review with JFM, so please keep your fingers crossed for me. We'll see how that goes. I must give absolutely huge credit and thanks to Samuel Harthen-Evans, who's my PhD student. He's responsible for the generation of all these beautiful videos, both in the lab and in the numerics. So many thanks, Sam, for providing them and being able to share them with you today. Okay, I now want to change focus slightly and discuss mode 2 waves. So Paul has done a great job of motivating this work for me already. So very quickly, mode 1 waves displace isopycnals in one direction only, and they can be waves of depression or elevation, whereas mode 2 waves displace them in two directions. They can be convex or concave. And it's thought that 90% of kinetic energy of nonlinear baroclinic modes is contained within these first two modes. So like mode 1 waves, mode 2 waves also have a surface signature associated with them. And recent work by Magda Carr in the Andaman Sea has suggested that mode 2 waves may be more prevalent than what people had previously thought. Okay, so in this paper, Magda Carr run their SAR imagery at a much higher resolution than what people have used in the past, and they think that lots of observations of mode 2 waves have maybe just been missed because their length scales are smaller than mode 1 waves. So how do we make these waves in the laboratory? Well, the difference now is in the generating volume of fluid. So the fluid that we put behind the gate to generate the mode 2 wave has a density of ρ2, where ρ2 is the average of the density in the top and bottom layers. And we're very careful to align the center of that generating volume with the center of the picnic line. So now when we pull the gate out, this fluid of density ρ2 wants to sit exactly at mid-depth, and we get a bulge of fluid that propagates into the main section of the tank. We're going to take a look at what happens when these shoal. So the bottom movie is from the lab again, it's the raw image, and this top image is the output from the PIV data. The color scheme is vorticity, and we're going to see velocity vectors overlaid on top. So this is a relatively steep slope, and you're going to see a mode 2 wave coming from the left. You can see that as it interacts with the slope, we get a buildup of vorticity in the boundary layer. The boundary layer separates, and we get a vortex generated at the bed, and the wave runs up the slope. We then get a bit of run down, some reflected signal, which then passes through the next mode 2 wave in the train that's coming in. If we look at a shallower slope this time, we get to see the interaction over a longer time scale because the interaction time is longer. So you can see that the bottom half of the wave gets flattened. It looks as if the top part of the wave has been split into two. And again, we see the generation of a vortex at the bed and the wave running up the slope. So we're able to measure this run-up distance in the lab. So we define it to be how far the fluid runs up the slope from the undisturbed top of the picnic line. And here I'm plotting the run-up length against the slope steepness. You can see that as we increase the slope steepness, we reduce the run-up length. And if we just think about it physically, that's exactly what we'd expect. Okay, so as the slope steepness increases, the wave has to work harder against gravity to run up the slope, and hence it's not going to get as far. These different symbols correspond to different amplitudes. So if we just fix the slope steepness and look at what happens as we vary amplitude, you can see that as we increase the amplitude, we increase the run-up length. And again, that's exactly what we'd expect physically, because the bigger the wave, the faster it travels. The faster it travels, the bigger its momentum, and the further it will run up the slope. So we can do these nice kind of simple physical arguments. So if we think about this point here, when the run-up gets to a maximum before it comes back down, if we balance net upslope momentum flux with a downslope component of the excess weight, then we can get this expression you see here as a scaling for the run-up length. And here I'm plotting the run-up length against the suggested scaling. All the different data points are from the lab, and you can see that they collapse quite nicely onto this straight line, suggesting that this is a good scaling to use for the run-up length. If we take a look at what happens now when we make the slope even shallower, so it's not as steep. So now you can see as the wave propagates along the slope, it has a tail associated with it, and that's because the density, it's the ratio between these layer depths is no longer unity, and the bottom of the wave is getting flattened out. The top of the wave looks as if it's splitting into two. Now, what we'd really like to see is the terminal phase of shoaling, but we can't in the lab because we're limited by that finite horizontal extent. We can, however, look at what happens numerically. So here I'm just showing you a comparison between laboratory observations and numerical simulations, and you can see we've got really good agreement between the two. The numerics gives us a bit more detail. So here we're plotting density, and the black fluid you see is fluid that's sitting at exactly the average density. So you can see that within the core of these mode 2 waves, we're getting these cusp-like structures. These are asymmetric Holmboe instabilities, and the observation is in keeping with some work that Schmidt did in a PhD thesis. And also, if you look at the vorticity field, you can see we can pick up short length scale features that we're unable to get from the PIV data in the lab. But of course, the main motivation to do the numerics is because we can extend parameter space. And in particular, we can look at what happens in the terminal phase of the shoaling. So this is what we see. We see that the wave degenerates into a mode 1 wave of elevation. There's a breakdown which lowers mechanical energy density, and the wave train essentially runs out of steam. This fission process is similar to the fission process we saw for mode 1 waves on shallow slopes. There's little boundary layer activity and no reflected wave signal. We can also vary the Reynolds number in the numerics. So here we are showing you what happens to the vertical velocity. So this is a Hofmolar plot. So we've got X and we've got time going in the vertical direction. And we're taking a time when the wave begins to interact with the slope. This top plot is for a Reynolds number, and the second plot is for double that Reynolds number. And you can see in the double Reynolds number case, the vertical velocity is higher than what it is in the single Reynolds number case. So this suggests that the larger you make your Reynolds number, the larger the vertical velocity at the bed of the slope. Why is that important? Well, in the lab, the Reynolds number is only about 10 to the 3. In the numerics, we can push it to about 10 to the 4, whereas in the field, it's 10 to the 6. So we'd like to try and infer what might go on in the field when we have a much larger Reynolds number. This suggests that vertical velocities are going to be more important in the field than what we've necessarily seen in the lab. So just to summarize, what have we found? Well, for slope angles representative of the ocean, we've seen that waves can dissipate their energy as they shoal by forming an oscillatory tail and also evolving into mode 1 waves of elevation. The waves were effectively destroyed by this process, and there was no wave reflected signal seen. The bottom boundary layer dynamics were negligible on these very shallow slopes, but the Reynolds number analysis suggests that the bottom boundary layer dynamics may actually be seen in the ocean. Moreover, features that we've documented here, so things like flow reversal and vortex formation, they have been observed in the ocean. And the bottom boundary layer dynamics are very similar to shoaling mode 1 waves. I've said that's what we'd expect. Why is that? Well, if you think about a mode 2 wave, it's just a mode 1 wave with a hat on. So we expect the flow features beneath it to be similar to the mode 1 case. We didn't see things like spilling, plunging, surging, or collapsing, which we did in the mode 1 case. And again, that's exactly as we'd expect because we've put that hat on. So we can't expect to see plunging, for example. And this work is also published in JFM. I must acknowledge Koen van der Waal. He was a visiting student, a master's student who came from the University of Eindhoven and did a great job again in the laboratory. So just quickly, very quickly to finish off, I just want to show you a couple more videos from the lab on mode 2 waves. So I'm going to show you what happens if we have a picnic line, which is located exactly at mid-depth in the tank. And what happens if we offset it? So if we move it up by 20% of the total fluid depth. So nothing else is varying. The generating volume of the internal wave is the same. The density difference is the same. The only difference between these two movies is the location of the picnic line. So in the 0% offset case, you're going to see a nice stable, symmetric, mode 2 internal solitary wave train. And there it goes. Let's now compare and contrast that to what happens when we offset the picnic line by 20%. Then you can see in this case, the wave has a tail associated with it. It's no longer symmetric, and it looks like there's some instability going on this lower interface. So in this case, we get something that qualitatively looks like this field observation that Schreier made off the coast of New Jersey. You can see in this case, we've got this mode 2 bulge. The wave's going from right to left, and there's a tail associated with the wave. There's also some asymmetry and some kind of disturbance on the lower picnic line. So what we found in this work basically was that if you offset the picnic line, that results in an oscillatory tail and asymmetry in both the wave shape and the stability of the wave. And if anyone would like to know more, that works in physics of fluids. And Ruud Hobers, again, came from Eindhoven and was a great help getting that work done in the lab. So finally, 2 more movies. We've looked at what happens when a mode 2 wave interacts with narrow isolated topography and also a broad ridge. We did this work in collaboration with David Deepwell, who was a PhD student of Marek Statzner's, and that's all in physics of fluids as well, if you'd like to know more. So what do I plan to do in the future? Well, a couple of years ago, I did some experiments looking at how internal waves interact with sea ice. So I actually worked in a cold lab, and we froze the top of the tank and tried to get measures of dissipation between different kinds of ice type. We had a really limited experimental campaign. We only got 3 weeks, but we managed to get a paper in GRL from those results. I'm planning on extending that work now with Sam, my new PhD student in the lab. We're going to be varying the upper condition in the lab. We won't be using real ice, but we want to try and see if we can learn more about how internal waves interact with sea ice or indeed with other floating structures. I've also been working with Marek Statzner on collision of mode 1 and mode 2 waves, and I hope to work in the future with Paul, Alex and Ricardo on these multi-humped internal waves. It would be great if we could get going in the lab and see how they work. So with that, I will finish. Thank you very much for your time and for listening, and I welcome any questions that people might have. Thank you.
Fantastic. Thank you, Magda. It's great seeing all the experiments you've been doing. Fantastic work. Did anyone have any questions for Magda? Feel free to unmute yourselves and ask directly, or feel free to type them in the chat and I can read them out. So we have one from Sergey, who thanks you for your talk. I wonder if you can experimentally produce internal tabletop solitons, so the ones where it's sort of this quiescent conjugate state, or their counterparts where you've got sort of a flip in the polarity. They appear at least as solutions to the multi-layer equations of stratified flows. If yes, what are the special experimental conditions you need to impose for this?
Yeah, so thank you very much for your question, Sergey. Great question. So John Brewer and his team did look at this. I think there's some papers like late 90s, early 2000s, where they really pushed the amplitude of the wave. So they made the waves as big as they could, and they were certainly tending towards these tabletop internal solitary-like waves. So just exactly the same formulation and generation method as I've discussed today, just have to push the amplitude really, really high, and you get this really broad, flattened out tabletop-like wave. Yeah.
Yeah, awesome. I had a question actually regarding sort of the tails of your mode 2 solitary waves, and also like the fission billows you see at the base. What mechanism or relation is there to the physical parameters and the period of these structures? Yeah,
so that's again a good question. So this was in relation to the fission one specifically, and these little boluses that you see going up the slope. So this works at a really kind of early stage, and we haven't had a chance to directly compare what we've got with with field observations, but there have been field observations of this. And there's also another paper being done on this where they've looked at the number of boluses that have been formed in relation to stratification. So I think the number of boluses, there's already a link there in the literature to the stratification type, but I would need to go back for sure to look at that. So we haven't yet got to the stage of being able to classify exactly how many boluses you're going to get, or how fast they're going to travel. We haven't done a classification of that yet.
Yeah. Okay.
Yeah.
Yeah. Thank you.
Could I ask a question?
Yeah, please, Victor.
Thank you. Very good talk. So, have you ever observed situation when you generate your wave and you got a vortex inside, as Davis Acreus observed many years ago? And this is first part of the question. And is it also a possible scenario of, if you wish, of breaking? So, of shoaling wave, it might develop a vortex inside.
Yeah, so again, thank you very much for your question, Victor. So that actually is what the motivation was behind this study when we first started doing it. So if you have that linearly stratified top layer,
yeah,
you generate an internal solitary wave where you have a core.
Yeah.
You have closed streamlines and you have this kind of overturning within your core. And
yeah,
trapped core waves, we were interested in seeing what happens when they shoal. So it's actually, the wave on approach actually does have this trapped core. And if I can just go back, you might be able to see it if I can.
Yeah. This is exactly my question. Yeah. So, yeah.
You might be able to see it in this observation. So in this particular one, so if you look at the wave on approach, I don't know if you can see it, but the core.
Yeah. Now,
yeah, you can see this kind of trapped core.
Yeah.
So that wave does have a bit of a trapped core on approach, but they're leaky. So even though we call them trapped core waves, some of the stuff does come out the back.
Yeah, but you have here a pretty steep slope. So what would happen if the slope is more gentle?
So again, let me just find the right slide. So then we'd be looking at this kind of stratification and we'd be down here. So we're predicting numerically that we'd still see fission.
Yeah.
So that's the prediction at the minute, but we could do with sweeping this parameter space a little bit more. But so far, we found that regardless of the stratification, if the slope is very gentle, you get fission regardless of what that incoming wave looks like.
So but you have got this core, and this core would. So how the whole structure will behave? So it's just So you have at least numerically you have answer to these questions. Yeah.
Yeah, we think so.
Okay.
Yeah. One data point, I guess that we could do more.
Yeah. Okay. Thank you very much.
Thank you.
Yeah. Do we have any more questions for Magda? Because if not, we will move on to the chair discussion.